Exploring Forest Resilience webinar series. Today, we are welcoming Janine Bösing, who is working at the technical Hochschule. How is it translated? Technical University of Rosenheim. And she will present us her work on topsoil cover engineering, optimization, and characterization. And I can imagine you work on soil, so we look forward to your presentation. And yeah, just get started. Now also a little bit confused because the start was a little abrupt, but this will be cut out anyways afterwards by Raquel. So we will just then start with your presentation, or okay. I will just say it again once and then it can be cut out. So very warm welcome to our Exploring Forest Resilience webinar today, which is presented by the ONEforest and the RESONATE project. We're sister projects and we initiated this together. And today we will be listening to a presentation by Janine Bösing. She's working at the Technical University of Rosenheim, and her presentation will deal with topsoil cover engineering, optimization, and characterization. And we look forward to your presentation, Janine.
Thank you. Let me share my screen. I'm not really familiar with Teams, so
you click on the right-hand side on the top. You can see, like, close to the red button which says leave. Exactly. Don't click leave. Yeah. Just click share.
Did it share now?
Yes, it's shared.
Okay.
And maybe you want to click to the next slide just to check if it works with the clicking
mode.
Yes. Yes, perfect.
Okay, thank you.
Wonderful.
Okay. Then welcome also from my side. Thank you for the introduction. I'm Janine. I'm from the Technical University of Rosenheim here in Germany, and I joined the ONEforest project in the beginning of this year, and I work on the topsoil cover engineering. That's my responsibility here in the project. And today I want to talk about the optimization and characterization of the topsoil cover. Topsoil cover in general supports planting operations in areas with high erosion risk and also regions subjected to temporary drought. And it has two functions. For one, it covers the soil, and for the second, it also has the capability of storing water. So through the coverage, we have protection against evaporation, for example, of the water that's in the soil, and also against competing weeds that would suffocate the new plant growth. And because we have the capability of the topsoil to be able to store water, it can be released in drier times, and so the plants have water that they usually wouldn't have if it's not raining that often. And here in Rosenheim, we are working with gelatin-based hydrogels, and now I will talk a bit about what steps we are doing for optimization of these topsoil covers. As I mentioned, our topsoil cover consists of gelatin as the main ingredient. We also then together with water make our topsoil cover. And we want to optimize the preparation of our topsoil cover. That means we want to cut down the time it takes us to prepare it and also the energy that it costs heating up our topsoil cover when it's still in a wet state. We want to optimize the application process. That means we want the forest workers to be able to apply the topsoil cover when they plant the new trees, which is of course a bit difficult because the topsoil cover is an additional weight that the forest worker would have to carry. So it might also be necessary that it would be applied separately by machines. Our topsoil cover is biodegradable. This is also a bit tricky because we want it to be biodegradable, but we also don't want it to be gone after like already 2 weeks. We want it to be there for a couple of years, 1 to 3 years. and then help the plant in that state and then be biodegraded and be gone from the forest, basically. Yes, our topsoil cover is there for the plant growth and also the plant health and the protection of these plants, and in general for protection of the whole forest. And we also want to optimize, of course, the costs for our topsoil cover. We have those three main ingredients: the gelatin, the wood fibers, and the crosslinker. And the least amount of ingredients we can use, of course, the least amount of costs we would have. Now that I've talked a bit about the optimization, I want to shortly talk about how we want to characterize, or how we are characterizing our topsoil cover. Firstly, we look at the hydrolyzation resistance of our topsoil cover. That means how resistant is our topsoil cover against water. This is mainly done by a partner university in Graz, Austria. They're doing tests there for us and give us the information then afterwards. We are also sort of doing it indirectly because we are doing weathering tests, which also gives us information about the water attack on the topsoil cover. And we are also doing water uptake tests that also give us information about the hydrolyzation resistance. Secondly, as I just mentioned, we are doing weathering tests. And about that, I want to talk a bit more in depth. Weathering resistance. For that, we have already prepared topsoil covers in different compositions. As you can see here, they are about 2 meters wide times 1 meter. And we have different types of topsoil covers with different compositions of the three main ingredients: the gelatin, the fibers, and the cross-linking contents. And the lighter colored samples you can see in between are from a partner university of Trento in Italy. They gave us some of their samples, so we are also testing them. We have installed this on a roof of one of our university buildings, and there we can see the influence of temperature, precipitation, wind, and also sunlight. And we have a weather station on an adjacent building, so from that we get all the accurate in-time data and can see what influence, what happened to our samples, in what time, and what was the weather like during that. We can have a closer look at, for example, these 4 topsoil covers. They are all 4 different compositions. And here you can see them on the day they were being installed. And then after the first 2 weeks of the experiment, here in Rosenheim, it was quite dry. We didn't really have rain in that time. And it was quite warm. It was, well, for Germany, it was between 20 and 25 degrees during the day and around 10 degrees during the night. And in that time, after those 2 first weeks, you can see that many of those topsoil covers
Janine, you got stuck for some reason. Did the others also notice?
Yes. Yes.
Okay.
Now
you're back,
we can.
Janine. I'm not sure if it's about your Wi-Fi. Maybe you can just maybe you can just go back to the slide before and start with the weather.
This whole one?
No. We saw the beginning already when you described everything. I'm talking about the next slide before you zoomed in.
Oh, this one then.
No, the slide afterwards.
Okay.
Yes, those and
okay.
And that's exactly where we got lost. So when you introduced this kind of second element after 2 weeks. And don't worry, in the end we can edit that out, kind of that the camera got stuck. And for us in the call, it doesn't matter at all because we are really listening, varying. It's super interesting. So just continue. I will stop talking.
Okay, thank you. Yes, after those first 2 weeks with mostly dry weather, we can see that all the topsoil covers show great sign of shrinkage. And we can zoom in, for example, into this topsoil cover. And because they are topsoil covers, we have some artificial soil underneath. And because soil varies greatly between regions and has a great influence then on the topsoil cover, we used artificial soil, as I want to call it. It's mostly sand, so it doesn't really have a strong influence on our topsoil cover because it doesn't have any living things inside of it. And here in this topsoil cover, we can see that there's great adhesion between the topsoil cover and the soil underneath. So the topsoil cover was shrinking because of the great temperatures, and it lifted the whole soil with it out of the box. If you look at this other composition of topsoil cover, we can see that that's not the case here. We have also shrinkage and deformation of our topsoil cover, but it's not connected to the soil. So the soil remained in the box, and we don't have that adhesion between the topsoil cover and the soil underneath. So that's an interesting result that we are seeing in the first 2 weeks of our tests with dry weather. And in this experiment, we just have uncontrolled components. We don't have influence on the wind, the sun, the temperature, or the precipitation. And of course, we are also interested in a controlled study. So we are also doing controlled tests where we have the influence of the sun, the temperature, and the precipitation in a lab setting. And for that, we're using a so-called QUV tester, and it's an accelerated weathering tester. And this reproduces damage caused by the sunlight, the rain, or the dew. And it just lasts days or weeks, and that damage outdoors would occur in months or years. And it tests the materials by exposing them to alternating cycles of UV light and moisture at controlled high temperatures. And we can have a look inside of this machine. If the video plays, then it will open. Yes, we can take the covers off. We see the samples inside of the machine. Here there are just some random example samples that you can see now from the outside. And if we take this cover off, we see the UV lights, how UV lights inside that represent the sunlight, and underneath there are sprinklers, and those sprinkle the water on the samples. So the samples are facing to the inside where they're facing the UV lights and the sprinkler system, and there we can test those in our controlled environment. And these tests we are doing there, they last for 6 weeks with our samples, and the outside tests, they last until the samples are gone or until the project ends, basically. So they're out there now, and they will stay out there. And this is, of course, way more controlled because we have a defined test and a defined setup with this. And this is the widely used weathering tool because it's a widely used weathering tool, the most widely used weathering tool. Now that I've talked a bit about the weathering resistance, I want to shortly talk about the mechanical properties we are measuring. And for that, we are interested in tensile strength. And tensile strength testing is a destructive testing process. And that provides information about the tensile strength and the yield strength. And this test measures the force that is required to break a specimen, and to which extent that specimen stretches or elongates before that breaking point. Here we can see some prototypes that I've tested before and after the tests, and we see that after the tests they are destroyed, and we measure then. We are also interested, of course, in the water permeability. That means how much water goes through the topsoil cover into the soil underneath. This is primarily done, again, by our partners of the University of Graz in Austria. They're doing this in combination with the hydrolyzation resistance because they sort of go hand in hand. Of course, the opposite, we are also interested in how much water can escape through the topsoil cover from the ground underneath. And this we don't want to happen, so we want to have some sort of evaporation protection. And for that, we have done water vapor permeability tests, or more like my colleagues have done this before I joined the project, so we already have data for that for our topsoil cover. And lastly, I want to talk about the water storage capabilities of our topsoil cover. And for that, we are doing different tests. For one, we are doing water uptake tests, which you can see here on the left. For that, samples get stored in water for specific amounts of time. And then we measure how much water gets taken up by those samples. And these first samples that we tried, they gained weight of about 300% of the starting weight. And we also measure the weight of the samples dry before the testing and after the testing. And through that, we also get information about the hydrolyzation resistance, because we are just using water. So we see the effect of the water on our samples. And we are also doing an aging test, where you can see a picture here. This is also where we store the samples in water, and then we heat it up to 80 degrees Celsius and see the effects of that, which is just an accelerated testing method. And for that, we also measure how much water do they uptake and how much mass do they lose through the testing process. I have some pictures here from pre-trials I did. We have the different methods that were used, the water storage for 3 hours and for 24 hours, and then also the aging process. The difference of the samples is that we have on the left a wood fiber content of about 10%, and then it gets higher, and at the end we have a wood fiber content of about 25%. And we can see that the higher the wood content is, the more differences you see through the aging process. We can see that all these samples with higher wood fiber contents through the aging wash out the gelatin and the crosslinker, and that's why you can see the exposed fibers in these samples. And with that, I want to shortly summarize what I've talked about today. I've talked about the optimization that can be done in the preparation, the application, the plant health and growth, the biodegradability, the costs, and also the forest protection capabilities of our topsoil cover. And we are characterizing our topsoil cover through hydrolyzation and weathering resistance, its mechanical properties, the water permeability, the evaporation protection, and the water storage capabilities. And now, of course, that begs the question, what happens after the optimization and characterization? Well, that's a bit of a trick question, because there's no real after optimization and characterization, because it's a cyclical process. We optimize and then we characterize, and then we've learned more, so we can keep on optimizing. And these optimized products then we give to our partners, and then they test them in field trials. And here you can see a sample that we've sent to our partners, and that's being used in field trials at the moment in Spain. And with that, I want to thank you for your attention. And if you have any questions, please feel free to ask them. Thank you.
Thank you very much, Janine. That was a really inspiring presentation, although the way you presented it. I didn't understand everything, I have to say, also because I don't have a background in forest research. I do know much more than I knew 6 years ago. However, there was still a little bit of jargon that I didn't understand, but very little. So congratulations on that. I know it's very difficult. I do have a couple of questions, and then I will, and I also see that Raquel has a question. I would start with a question of understanding, and then a kind of more practical question. Why do you work with wood fiber? That's a kind of thing that I just want to know, because it doesn't occur to me. And also in the Resonate project, we don't do a lot of technological work. I know in Rosenheim you do a lot of kind of technological work, like you kind of combine the forest and technology, and we do this a little less. So that's why I'm curious. And why is fiber the good material to do the testing, the trials?
Well, I think the wood fibers are sort of a reason why Rosenheim is in the project, because that's our background. We we are working with wood. That's what Rosenheim University is good at. And the wood fibers, well, for one, they can store water, and for two, they can also give strength to the material because of how they are built. And with the gelatin and the crosslinker all together, they can make a very sturdy material that's sort of like, yeah, it feels like wood, sort of, not really, but it gives it like structure and durability.
Okay, that makes sense. And just to kind of understand the overall context, or to check if I understood the overall context correctly, you do this because you want to see how this mixture of gelatin and other materials can protect the top cover of the soil from drought, basically. So how would this, okay, that part I got completely right. Okay, that's good. But how could it, and I also understand that you kind of send the material to the fields now, and that they are trying it in the case study area. But would this also kind of, imagining that the kind of combination of materials that you chose and that you're trying to optimize is the kind of like perfect fit, and it really helps the forest soil to store more water, and to kind of get then also for the trees to get less prone to drought, and so they would suffer less in the kind of climate that we're expecting in the future. Would this work large scale? Is this kind of what you imagine in a long term, that you would use this? Because I can imagine, like, from a technological point of view, it's also quite advanced and a little complicated.
Yes, that's the idea. At the moment, we're just doing it in those discs that I've showed. Like, that's the ones we apply now. But we also imagine, because it's sort of liquid when it's not hardened, so we could apply this liquid larger scale in the forest on the ground, and then it would dry and harden there and be able to protect the forest. That's the idea. But we haven't done any large scale testing like that yet.
But you could do you could kind of have a suspender, like you could do it in a similar way, like because I know that they're doing it in another project with seedlings now, that they use the kind of similar machine that they use to pump the water, like when they're fighting a forest fire, that they use it to kind of spread the seedlings all over the forest that was damaged by bark beetle, and then clear cut. And so it could work in a maybe similar way, that it would be kind of sprayed around. Cool. Okay, I really like that idea. Now I will hand over to Raquel, because you also have a question, right?
Yes, well, actually was the first one that you have asked, but my second one will be if this type of topsoil will be also suitable for Mediterranean forests, because they are more dry soil, and we have more water restrictions, and we have problems with fires, etc. So also the management of the forest now is it's less managed than before. So I don't know if for this region could be also an option.
Yes, our idea is that it would be applicable to all the 4 different regions that we are having in ONEforest as test regions. And yes, we already have some field trials being done in Trento in Italy, and some also, yes, in Spain at the moment. So yes, we hope that it works in different regions.
Thanks, Janine. There's a question in the chat, because Annikin cannot join with video and voice, but she liked your presentation very much, and she her first question is that if she understands it correctly, that you now test the soils, and then in the case study areas, it will be tested in forest stands. And then she asked, do you have any insights in those stands, like what kind of tree species, and what are your expectations, or do you have a hypothesis how this will work? Because I can also imagine that you have different species composition in the different case studies, right?
So far, what we've been working with, I don't know what they use in Spain, what plant species, but in Italy we're doing trials with tomato plants because they grow really quickly. And we've also already applied it here in a forest in Germany that I know of. At the moment, we're doing no specific plant differences, that we are making different topsoil covers for different plants.
And I mean, I can imagine that it will be used first, like when it's kind of used more large scale, for forests that are more prone to drought, obviously, because they need it more than others who can deal better with the kind of longer dry periods.
Yes, and also here in our region, in the Alpines, we also want to apply it. We have this problem of erosion that if we have our mountains and hills, that if there's not enough trees with the root system, that then the soil gets eroded. And we also wanted to be able to protect that area by bringing it, by applying this topsoil cover so that rain and wind cannot erode the soil that much.
Really cool. Ankin also got really excited. So if you could later on put the names of the people who work on that topic at Uni Graz into the chat, that would be really great, because then Ankin is planning to go there and check them out and look at the soils, because she's also based in Graz and at the university, so it would be cool. And then Julius, you also have a question.
Yes, actually also two questions. So my first question is, do you know if it's actually applied somewhere in more of a context of business, like, or is it that kind of a brand new idea that it's still in testing?
Do you mean ours specifically or in general?
In general, because I haven't heard of any topsoil cover yet.
I also don't have heard of any specific, but that doesn't mean that it doesn't exist.
Okay. My second question would be, do you think that when it's weathering, like when the cover is decomposing, would it weather into the soil below, so that the soil below might even have better properties afterwards and could maybe also build up a humus layer, which is more sustainable, so that that the product kind of weathers into the soil and then the soil is better in the end, or?
Yes, with with different compositions, have you seen where we have the strong adhesion from the topsoil cover to the soil underneath? That for sure, because that's a more liquid composition. So when you apply it, it already seeps more into the soil. So there's definitely then some difference in the soil from before and after. With the drier compositions, where we have a higher content of wood fibers, there it's a bit more difficult because there's no real adhesion. So the question then is, does it get biodegraded by just wind and rain and animals, or does it then also some parts go into the ground? That we will see with our weathering tests, if in the end there's some parts that are still there on the ground, or if everything just got washed off.
Nice, thanks. That sounds like a great project and might be really helpful in the future.
You're mute.
I completely agree. It's a very, I think, promising approach, and I also really curiously followed the beginning of your presentation when you said you were kind of struggling to find the right composition, but then also kind of making sure that it doesn't degrade too early, but also not too late. So it's really tricky research. Is there any other question from the audience? From Reno or Simon? Anything you still want to know? Okay, then I think it would be cool if you could still put the contact of the people at Uni Rosenheim into the chat, or I can also.
You mean the people of Graz?
Yes. If you could put that in the chat, that would be great. Just the names of 2 people or 1 person, and then Anniken can find them, because it's interesting to see that there are people at your university who do this stuff and you're not aware of it.
Yeah.
You can just pop by and check it out. So I envy you, Anniken. And yeah, once that's done, I would like to, thank you very much. Thank you very much, Janine, for the presentation. It was really excellent and quite inspiring. And I think, Julius and I will somehow introduce that in when we meet in a couple of months in Croatia, because I think there's more room for or there might be more room for engagement with ONEforest and Resonate also on the case study level. So I think some of the techniques might be really also interesting for our case studies to at least be aware of, so we can kind of do a little more knowledge exchange also on those elements of the work that can be beneficial then for both. So thank you very much. Is there anything that you still want to say, Janine, or are you okay? Wonderful.
Thank you.
Then I wish you all a very nice rest of the day.